So next to last presentation today is from the Electrical and Computer Engineering Department, and it's titled Reconfigurable Space Computing for Collaborative Robotic Environment Applications. Sponsored by NASA and Lockheed Martin, the Reconfigurable Space Computing Lab aims to create a team of unmanned aerial and ground vehicles that can communicate with one another and achieve mid-air drone docking for the purpose of power consumption and information exchange. The project team is working with post-quantum and lightweight cryptography to test the most efficient power usage to ensure that the data transmitted between vehicles is secure. I now invite the Electrical and Computer Engineering team to share their presentation, please.
All right, hello everybody. We are from the Reconfigurable Space Computing Lab, and we are talking about our Reconfigurable Collaborative Robotic Environment today. Our advisor is Dr. Muhammad Ali, and my name is Billy. This is Akif, Christine, and Michael. There we go. I don't know, we're on the wrong slide, my bad. All right. So just a little outline of what you'll see in this presentation. We're going to be talking about our motivations for the project. We're going to talk about our collaborative robotic environment. We're going to be talking about our unmanned aerial and ground vehicles, as well as our 2 encryption methods, and finally the drone docking part of our project. And so our main goal for this project was to create a collaborative robotic environment that addresses power consumption and secure communication. And the necessary research and development for this was to ensure encrypted communication, do a power consumption analysis, and then finally figure out a way to have drones dock successfully.
So first we're going to talk about our collaborative robotic environment and what that actually means. Initially, we have our first set of UAVs and UGVs that use lightweight protocol communication. This is also with another set of UAVs and UGVs that are also using lightweight protocol communication. The UGVs will be using post-quantum protocol communication, and the rest of the system will also be using lightweight communication. Post-quantum is used through the UGVs because it's more energy dense, and lightweight communication is less energy dense, which means we'll talk more about it in the next few slides. But, so going on into our unmanned ground vehicles, we have our first one, Curie, the UGV. She is equipped with a Raspberry Pi operating system and a GPS for GPS location data. This is extremely important because it helps us find exactly where it is, and the Raspberry Pi is used to run our encryption algorithms. She's also equipped with an object detection system and a landing platform for drone docking on the ground. We have our second UGV. It is equipped with a pink Z1 FPGA board, which uses Xilinx to control the motors, and a TP-Link Wi-Fi router, which is used as our central communication system. We have also for the UGVs, we have Curie has an LCD operating system. It's a touchscreen operating system. We're using this so that we can actually remotely connect to the UGV, upload programs, and change without having to actually physically have the robot in our hands. We also have an object detection system. It has a LiDAR long-range detection system, a Pixie 2 camera for short-range detection system, and a missile defense system. The missile defense system is meant to protect the robotic environment. We have our unmanned aerial vehicles. The first one is enabled with ARM. It's an ARM-enabled UAV. It's called the NavQ+, and we also have a Pixie 2 camera. That is used for object detection and also landing. We have our second FPGA. It's called Red, and I think you can see why. But it has a pink FPGA board, which also uses Xilinx to run. And then we have an OpenMV camera. This is a machine learning camera that we use to land on the platform that you saw on Curie. And then next we'll talk about our XMSS.
So for securing our robotic environment, we decided to go with the Extended Merkle Signature Scheme, otherwise known as the XMSS. XMSS is a post-quantum state stateful hash-based signature scheme that is designed to secure against quantum attacks, such as utilizing algorithms such as Shor's and Grover's algorithm. So, with quantum computing becoming more and more common, we decided that the XMSS is our best hope for securing our drones and ground vehicles.
And over here we can see a comparison of our XMSS algorithm compared to an RSA. It's an encryption and signature scheme. So we actually compare, since XMSS is a signature scheme, we're comparing it to the signature scheme of RSA. As you can see, RSA at 2048 bits has a larger key size, and it takes longer to generate, while for XMSS it takes less key size and less time to generate. We can also see on the left side right there, this is just some calculations that we do for each hash function. It uses a Witnitzer one-time signature chain, and it calculates our root and our WOTS.
So here we have our execution of our code. We send a hash-based message. We send a message, hello. We generate the public and private keys, which we then make it go through the Merkle root, and then we sign it using the Weinitz one-time signature, which we then traverse back for verification using the Merkle path.
All right, so why lightweight cryptography for this project? So lightweight cryptography is a special school of thought in cryptography which essentially focuses on lower power usage and low resource usage, which is really important for this project because we have quite a few UAVs and ground vehicles that are all operating on batteries. So the specific lightweight cryptography algorithm that we chose to use is called Tiny Jambu. It's based on the Jambu encryption algorithm, which is an open source algorithm that you can go and read the documentation on. It's really great. But essentially, it's a stripped down version of that algorithm, which provides most of the safety and security of the Jambu algorithm without all of the resource usage and power usage. And it's an authenticated, secure, it's an authenticated, secure cryptographic algorithm, and we're using a 128-bit implementation.
All right, so we just went over our two UAVs, two UGVs, how they communicate, the security between them, all that good stuff. But we also want to implement in our collaborative robotic environment 2 drones mid-air docking as well. So we know drones have a short flight time, so we were thinking if one is dying in the sky, how can we save the information it picked up, potential for charging each other in midair and all that stuff. So we'll show you some of the prototypes that we went through. We had a lot of them, but we'll show you the key ones. So the very first one, his name is Penguin. Spoiler alert, he did not fly. We wanted to have a bladeless design. So in that cross-section that you see up there, that is the airfoil design we attempted at creating a bladeless design for the drones, because at first we wanted them to dock side by side, because the blades would cause obstruction if we wanted like 2 drones to land side by side. One of them could hit another one and completely break it. But yeah, so this one proved unworthy. Okay, the next one is Joker. So we still wanted at this point to have them dock side by side. So we implemented an air duct design, so right here. And right there we have a fluid dynamics simulation, and it showed us that this one did fly, but it had a lot of turbulence, and the load test that you see on the bottom in blue, it showed that it had an imbalance. So whenever it would fly at a high enough throttle, there was oscillations on the arms, and the drone would just spin in circles very quickly. So even with the finest PID tuning, this one just wasn't stable enough to genuinely try and dock with another drone. So on to where we're at right now. We got our boy Zombie. He has died and come back to life so many times, but he is the most, we've got the most faith in this one. So the purpose of this one, at this point, we switched it, docking side by side. We are docking now this small drone on what we're gonna call a mother drone. I'm gonna go in the next slide. But we could see from the fluid dynamics on this one, that it is much, much more stable in the way that the air is flying. There's not that much turbulence. And this one did fly, and it's got everything it needs. So the next one is gonna be our mother drone. His name is BAD, don't be fooled. His name is a big autonomous drone. And so what we got on the right side, what we got on the right side over here, he's made of styrofoam. He's very heavy, so 2 issues is, yes, the weight. The second one is the weight distribution. What we first wanted was our docking placements to be on the sides, but we realized that that weight imbalance, all the sensors, gyroscopes, the Pixhawk, everything on there, would not be able to factor that in real time if another drone were to land just on one side. So what we did for our new design, to make it more lightweight, it's gonna be made of carbon fiber, and we want the landing station to be in the middle, so it's more easier of a change to the roughness of a small drone landing on it. And this is the mother drone that is going to be receiving all the charge and information if a drone is dying in the sky, like I said earlier. This one's gonna be retaining all of those information. So now on to the actual charging process. We want to dock the drones midair, we're gonna charge them. So what we have on the Zombie drone is we have 2 4-cell LiPo batteries. Those 2 4-cell LiPo batteries, one of them will actually be the one powering the small drone, and then the second one will be the one that's actually charging the large drone. Because we can't expend all the energy charging it, expect it to fly off. It's just gonna die and fall in the air. So when it lands, it has a Pixie 2 camera for precision landing. It will land on copper plates that are on the mother drone. That is the landing station in the middle. And the Raspberry Pi that is on the small will detect that it landed in the correct orientation so that we can actually start the charging process. And that will flip, those 2 relays are the ones that are the switching circuit that will switch between the 2 battery packs that we have on the small drone. So it will go from the 14.8 nominal voltage on the LiPo battery on the small one, and it will go through the buck converter, and it will step it up to 16.8 volts. That is going to be the 18650 spot welded battery pack we have on the large drone. We chose 18650 batteries on the large drone because it has a much higher energy density, so we can genuinely charge it up more. We chose LiPo batteries for the small drone because it has a higher discharge rate, so we could charge quicker. So on to actual flight time. Again, we all know drones have a very short flight time, so we want to also fix that. And we acknowledge that we are charging batteries with other batteries. There is potential for combustion and just smoke and sparks and hazards. So what we're doing is we first started by testing incrementing current from a power supply, kind of emulating the LiPo battery that the small drone would have. We incremented it by about 1 amps, and we found an exponential decrease in the time it would take to charge the large drone. And then on the right side is like where we're starting off with the small drone. We expect, given the weight of, I believe it's 1.35 kilos, we expect the flight time to be around 2 minutes and 25 seconds. And then after charging the large drone, assuming this drone, like let's say it's about to die, it only has 2 minutes left, we'll land on the large drone, charge it, then the large drone would be able to have an anticipated 8-minute, I believe 30-second flight time is where we're at right now. Again, this lab, everything keeps changing, keeps going super quickly, so a lot of these numbers are changing by the week, and we're changing what materials we're using and all that good stuff. So, and then all you can see on the bottom right-hand corner are the equations that we used for the basis of all these calculations. So, concluding, I know this is a lot, this is essentially a visual representation of what we want from our collaborative robotic environment. So, the small one on this small section on the bottom is what you saw earlier in the encryption section, but now that you learned about the mother drone, Zombie was a prototype to make sure that docking would be able to happen and the charging process and everything. But ideally, we'd want, this is Red, the one that Akif was talking about earlier. We essentially want that one to transition to be the UAV that would land on the mother drone. So, and we want all of the communication between exchanging information, charging, any of that stuff to be able to be secure. So that's why we're doing all this encryption, but drones do not have their power life, and just how long that they last is not that great. So that's why focusing on the power consumption, tracking power consumption, and the encryption between everything, just so they can recognize each other and In the future, in our research and development, we are going to try and make everything autonomous so that no human intervention needs to be made. So this is our collaborative robotic environment. And then again, these two are the ones that we were able to bring by the lab. And then, yeah.
And we just want to thank NASA, Lockheed Martin, also the College of Engineering here at Cal Poly Pomona for supporting us. And thank you very much, everyone.